What is an image? What is a video? This lecture aims to introduce you to the fundamental principles of the same. Image is a two-dimensional representation of a three-dimensional object, and a video is the multiple frames put together, so the video has got the time dimension. The applications of image processing include image enhancement, image restoration, and image compression. These are used for telemedicine, entertainment, video games, virtual reality, and whatever else. What is the image? What is an image? A two-dimensional function where the function of intensity at every point in the image is the representation. And let's consider gray scales for the time being. Yes, you can have color. For different colors, we'll have the same process. So for gray scales, I have one function of x and y, each point the intensity. If I digitize it, I get the digital image. Now, that is quantized. And let's see what that means. Now, each image, each point is a pixel, short for picture element. And each pixel is the smallest element of my image. The more the number of pixels, the greater the resolution, the sharp is the image. But that means the more the amount of memory I require. Now, I can have more number of pixels, horizontal and vertical. I can also have greater representation of each point, and that can be 8 bits or 16 bits or similar. Now, this is my quantization. This determines how many grayscales I would have in my image, while this would represent what is the size in that image, what is the density of the pixels. In the old-fashioned language, that is also referred to as dots per inch. Dots being each pixel. Now, this is what we change when we change the resolution of our screens on the computers. Say, for example, if we want to go from 640 times 480 to change to, say, 800 times 600, or whatever is the regular nomenclature. Now, what have I done is I have increased the number of pixels, and from here, which would mean that my resolution has improved. But of course, that would also mean that my amount of memory that I require to store the same image has increased. Try changing the resolution on your computer screen and see what you see, what you observe. Also observe what happens when you change the number of bits you use to represent your image. A digital image, all it is a function of the rows and the columns, and a matrix function from F naught naught on the top left to F R minus 1 C minus 1 bottom right. The more the number of rows and columns, the greater is the density of the pixels, the greater is my resolution. Each point here is a pixel. Along with that, I would have the quantization, how many bits I require to represent each and every pixel. And that would determine how many grayscales I have. Now, we'll quickly have a look at what are the most commonly used image parameters in today's computers. So we can have the number of rows, R, number of columns, and the number of grayscales. Grayscale 2 obviously represents a binary image, just black and white. While this is where you have a large grayscale density. Here again, you're going from the 256, which is at the bottom resolution level, going right up to 1320. And in the rows. Actually now this can be going higher also.
Okay.
When you are processing an image, the output image would be influenced by the input image point to point. So we are operating on each point. Whatever we are doing, changing the image, that output point is dependent upon the properties of this point and this point alone. It may be because of a region, a local region, that influences this point. Or it may be that the entire image has an influence. This is referred to as the global, this the local, and this point-to-point operation. An example of this could be that if you would like to change the entire intensity of that image by simply adding something to it, adding the mean to it. So you take that entire image quality and each and every point in this is influenced by that. Here it is more like a little region you are influencing. This could be when you're doing things like edge detection or when you are working on a specific small region for the purpose of zooming in, for example. And this is, and of each point to each point has a different operation. This output of this is dependent only on this particular point. Now, let's consider what are these neighborhoods for the local region that we were referring to here. They can be at any folds, but the commonest ones are where they use 4-point operations, 8-point operations, and 6-point operations. The common ones being the 4 and the 8. The 4-point operation is that you have the actual point is this one, and the 4 points that are closest to that, which are touching it, have an influence on the output. So when you are generating the output of the image, that point in the output image this particular point in that image is influenced not only by this point, but a result of all the others around. So it actually creates a kind of an averaging effect. Now here what is happening is that this point would appear in the output, but influenced by all these 8 points and the center point. Here, this point would be influenced by the surrounding 6 points. This has certain advantages, but results in complexity. Zoom in, zoom out. It is an operation that all of us do with images all the time. Now, what is it that we are doing at that particular time? We've got the matrix, which we refer to the fxy, and we are expanding that matrix to be able to give that impression that it's become bigger and we can see the image bigger. How do we do it? The number of methods. The averaging method, which is the block method. We can use the convolution method. And there are others. So let's start with averaging.
Yep.
Now let's take the simplest example, which is the averaging. What does it do? I have the original image, 8 for whatever, series of numbers. I want to now double the size, enlarge it. So I stuff between each of these, I put the average of the two. So between 4 and 8, I put 6, 4 and 8, I put 6. And then I do it the row-wise. So I've got, again, 6, 6, and whatever else. I have now generated the image, which is the zoom in of the original image. This does not contain more information. It just appears bigger. And we would like to try and make sure that it doesn't look smudged. The other technique which is used for zooming in is convolution. I use a standard mask. I take the image and I convolve this with the image to get my zoomed in image. So what I have here is that I would like, typically, this is not the only mask, but an example of a mask, I would like the influence. I have the original image, 3 on 3, let's take any example, 3, 8, 4, 2, 5, 8, 5, 2, 2. I want to now zoom into this image. What do? I build an image matrix like this. So it is etc. In between, I put zeros. I have my convolution mask, which is 1 in the center, half at the closest points, and quarter in the farthest points of the neighborhood. Now I convolve this with this, and the convolution of this results in 1 point. And I will move the mask like here, and I'll get the next point, etc. So what would be this point? I would like you to calculate. To give you a hint, 1 by 4 plus half times 0 plus quarter times 8, etc. All the 9 points added together. And you might have to normalize this for the intensity. But let's not worry about that right now. Let's get this point. This way we can convolve and zoom in, and have a much better zoom in quality. These different masks are available, and people have invented these for various applications. Images need to be operated upon. Things like masking has to be done. You need to remove backgrounds. You need to multiply, change intensities, do all those operations. You need to zoom in, zoom out, etc. There are a number of algebraic operations that are done on the images. The common ones include the addition, the subtraction, multiplication, and the convolution. A simple operation for images is image subtraction. One of this could be when you're subtracting one frame from the other frame to identify the motion. Let's have a look at this. You have one frame where there is a car and there is the other car which is moved. Everything else is remaining constant. So by subtracting one frame to the other frame, what we get is the section which represents the motion of the car. Motion template is formed by this. There are a number of mathematical operations that are conducted on images for various applications. Some of them, things like multiplication, etc., would be simply to change the intensity of the image. One simple operation, an arithmetic operation, is a NOT operation. Let's see what it does. Here is the image. Now that, using NOT operation, we've got the reverse. And in this particular case, because the human eye perception is that we see black better than white, we can actually read the writing in the back, which you couldn't have done here. Another operation is the AND operation for the purpose of masking. So we've got this frog, we masked it with this mask, we get this. The alternate is the OR operation. Thanks for participating in this lecture. The next lecture will be to cover more aspects of image processing, especially related to telemedicine. Now, please go through my lecture on the S-Drive, which is Image Processing for Telemedicine and Multimedia, AAAT 1417, Image Processing 1.